What I'm going to talk about, nanoscale quantum calorimetry with electronic temperature fluctuation. This is something done, most of the work is done by my PhD student Fredrik Brange, and this is done also in collaboration with Bayan and Jukka, who are sitting in the audience here. Aha, did I do that? No. Okay, and okay, and we just put it up on the archive, so it appeared yesterday morning, so it's fresh from the oven here. So that one is not okay. Well, that's fine. Yeah, interesting. Yeah, let's see if that works. I think we can manage. So the outline of the presentation is like this. So let me first say something about calorimetry of heat pulses, a little bit about the development over the last years on fast and sensitive readouts, measurement of temperature, and then something about the holy grail here, how to reach sub-milli-electron volt detection of heat pulses in nanoscale systems. And then I will spend quite some time on discussing what we are proposing, a way to do this in a type of system that Jukka and others have looked at before, similar type of devices, and then describe this as carefully as we can. It's a normal superconducting setup where we want to do a statistical analysis of the energy transfers in this system to learn more about what the limitations are. And then I will go into something about the temperature of the system and how it fluctuates. I will motivate this, why this is important, and try to do a full statistical description, and in particular focus on the cumulants of this, which might be measurable temperature noise, by the way, would be the first thing that one would try to go for as the next step after measuring the average temperature. And then also something about the third cumulant here. No, right, this was the... Right, so let's start at the first part. Very overview-ish here. So I just try for you who are not familiar with this, and I wasn't also until a couple of years ago. I just look at the Wikipedia, our source of knowledge here, to see how they define the calorimetry. And this is somehow the science of measuring heat transfer due to looking at changes of state in state variable of a system. And what I will be concerned with here is to look what is the energy that a system has gotten or has been transferred to the system, and that is read out by looking at how the system temperature is changing. So here you have the simplest minded picture. You have some system, a block of concrete, and then you heat it up during some time, and then you measure simply the temperature of the system, and then you will have a curve that you go from some lower to some higher temperature. So there is a difference in temperature, and then if you know the heat capacity of the system, you can calculate the absorbed energy, or if you know the energy, you can get the heat capacity and so on. So this is the very basic principle of calorimetry. I also have the word quantum in front of, and quantum calorimetry is typically coined as a way of detecting the energy of individual particles. So what we had before was really a block of something, putting a fire onto it, and this has been really worked out in detail in particle physics. So this is a very schematic picture. So you have some absorber where your particle bounces in and deposits all its energy, and this absorber is then coupled to some background, some bath, which is kept at some fixed temperature. And when you measure the temperature of your absorber, you will now have a little bit different from before. There will be the same jump when the particle hits, and then you will see how the temperature decays when the energy is leaking out from your absorber out to your background bath here. And this you want to have now such that if you do this for particle detection, you want all the heat to be gone before the next one comes, but you don't want it to go so fast so that you have no chance of reading it out. So in the ideal case, you can just write it like this. There's a simple circuit model of this. There is a time-dependent temperature, it's a thermal circuit, there is a thermal conductivity and a thermal heat capacity, and then there is this bath at a certain temperature. And well, if you then can read this curve out, you can then from the jump here, you can just deduce the particle energy that came in. And as I understand it, and I'm definitely not an expert on this is really a standard method when you do experiments in particle physics, that you also want to know what is the energy of the particles coming into your experiment. Then I would guess that these people are probably not interested in micro and milli electron volts, but it's rather mega and giga electron volts. So it's a different science doing these things in particle physics, but the idea is basically the same. Oops, there was a double, I guess. If I move to the area where most of us are interested in what's going on, then it's the question of doing this with small solid state nanoscale mesoscopic systems. And then there are a number of early experiments in the 90s where people used kind of similar setups that I'm going to discuss here, where there is a normal metallic absorber coupled to some system, some antenna, collecting some radiation coming in, and then sending it onto the absorber, absorbing the energy, and then measuring quite often via superconducting tunnel junction to measure the temperature. And then it's important that this is in a regime then when it's a hot electron bolometer. So with hot electron, it's meant really that the electron gas is essentially in equilibrium at a given temperature all the time. So there's a burst of energy, and very soon, in a very short time scale, the temperature becomes well defined because the electron interactions makes them to relax in the system. And there are some pictures here. There are some references worth mentioning for X-ray detection, and then it was an improvement doing a fast radio frequency readout of the temperature, and then also some improvements on sensitivity. So this is, I can maybe mention this, sometimes there is a mixture of bolometers and calorimeters, and as far as I understand it, the bolometer is more of the approach of measuring the power of something coming in, so that you see a constant change in temperature when you have a power on and power off. While in a calorimeter, you really want to look at the energy of a heat pulse deposited over a certain time. And here it's, of course, it's kind of in the middle, if you want to, because it's a certain, in these experiments, there's a certain power on for some time, and you see a change in temperature. But you can also do some time resolved stuff by, when you turn off, you see how long time it takes for the heat to leave your system and to decay, and therefore you can also get these time constants out for the escaping energy out of the system. I'm mentioning here this has been largely driven by space applications, and I guess there are many people in the audience here, or at least a few of them, who know this much better than me, so therefore I'm not even pretending to give a complete overview of this, so there's also not much time. When we were motivated from the theory side and in discussions with the ALTO people a lot by the recent progress in ALTO, and I realized that there are more people in different places who have been doing nice progress on these detection things also over the last years. I'm now just therefore mentioning a couple of ALTO references here. And I think I can summarize the development by saying that, okay, it gets faster, the thermometry, it gets more sensitive, you can go to lower temperature. As you will hear from Bayan's talk here on Friday, there are also better non-invasiveness. In principle, you cannot measure temperature without disturbing your system, but you can do it better and better. You can go to smaller absorber volumes, so you have a smaller heat capacity, which is also good, and you can also go to lower temperatures and so on to reduce some background noise here. So there is a drive towards better and faster and smaller systems. I'm just listing a couple of parameters, roughly collecting what was the state of the art in these papers here. So the heat capacity is 10 to the 3, 10 to the 5 of kb. The time is of the order of microseconds, and then you have a temperature. And then I'm mentioning here that this is really the effective temperature that the absorber, the electrons in the absorber sees. You can probably get your base temperature further down, but it's another issue of keeping your electrons when they are really in equilibrium, waiting for the next burst to come to keep them at a low temperature. So this is the effective bath temperature, which I'm citing here. And the holy grail, or the thing that you really would like to go to do, is to extend this approach with a full time dependence and really use this to detect energies which are in the sub-milli electron volt regime, really down to 100 microelectron volts if this is possible. Because then you could in principle start to do a real-time detection of, for example, a microwave photon coming out of a qubit. And you could also do this to detect individual electrons tunneling in a system, if they are tunneling across a superconducting gap, tunnel barrier, so that the energy is put by the superconducting gap. So then you can do this as a way of counting and studying heat processes in time when you are reaching these type of regimes. So that would, of course, be very interesting fundamentally and a very nice technological advance also. So that's the, let's say, the goal that we have at the back of our heads when we are doing this here. Okay. Now, as you all know, this is a conference on quantum thermodynamics. When you go smaller and smaller, fluctuations become more and more important. And in this case here, what I showed before was the ideal case is when you don't really worry about any background fluctuations, you just have your temperature peak. But you know that even for temperature in this state in your absorber, there is something that looks like a fluctuation-dissipation relation that tells you if there is some thermal conductivity between your heat bath, which in this case typically are some phonons in the metal of your absorber, and your electrons, then there will be fluctuations. And you can write down this type of fluctuation-dissipation relation and estimate how large these fluctuations are. And that will definitely depend on your capacitance of your system and on the temperature of your base temperature here. And you can also then estimate the signal-to-noise ratio. So how large is your temperature jump when there is an incoming energy, and how large is the amplitude of the fluctuations? And as a rule of thumb, you would, of course, like this to be rather large. Just to illustrate this a little bit here, to put some meat on the bone, I will come back to the system we have been looking at, but these are just some Monte Carlo simulated time traces on how things can look. So the red one here, now we are pushing parameters, as you see, down to 200 microelectron volts. So that would be typically the gap of an aluminum superconductor, or a 50 gigahertz microwave photon. And then you have this 10 to the 3 kb for the heat capacity, which is a really low number. And then again, very low numbers for the bath temperatures here, 5 millikelvin and 30 millikelvin. And if you really push it down to 5, you have a signal-to-noise ratio of 15, and then you see the red curve. Well, it's not bad, right? I mean, this is essentially how it looks. But if you then go to 30 millik and have a signal-to-noise ratio which is, well, above 1, it's getting not so easy to maybe see what's going on here. So what this tells us from this initial studies is that we really need to worry about fluctuations of quantities in this when we go to these energy scales and these small systems. And one important thing, which I guess our experimental collaborators will have to fight with, is to look at some noisy signal and say, okay, what information can we get out? What is the bandwidth of the detectors? Can we resolve this peak? What's really going on here? I am not really taking this path now here. So what I'm instead doing is that say, okay, fluctuations are important. Let's then look at this type of system where you might have a chance of doing these type of experiments and investigate the fluctuations appearing and trying to characterize them and understand as much as possible what they do to the energy measurements in this system. So that's the first step that we took, or we take when we do this, is to realize that maybe in contrast to a number of these calorimetric experiments with elementary particles, well, it depends on what things you are doing. Typically, if you're looking at the nanosystem, you don't really know, in many cases, when your energy pulse is coming, and you don't really know how large it might be. There are thermal fluctuations, there are quantum fluctuations. So in general, you will be looking at some time trace, and you can actually have particles jumping out of your absorber, giving you a negative temperature spike here. So typically, this will just be some time trace of spikes, and if you're if you're lucky, they are well separated and so on, and you can resolve them. But what we said that a starting point for looking at this, which is very important, is to treat now all the fluctuation events in our system on an equal footing. So one thing is the fluctuations due to that you are sending something, you are injecting some energies into your system. And on top of that, the other type of events which were causing all the background fluctuations are these, let's say, discrete energy transfers between your absorber and your bath. Because eventually these are also quantum events, typically phonons being annihilated or destroyed, and then you are shuffling energies in some quanta between your electron gas and your phonons in your absorber. So all these ones are treated stochastically. And the formalism for this, well, I'm just pointing this out, that we are looking at this statistically. It's a distribution of probabilities, and the natural quantity for us here is to do this over a certain time window here. So when we have a number of these pulses occurring, and then we can write the total probability of having a certain total energy being moving in or out of the absorber during a certain time interval, and we write this in this form where there is a so-called cumulant generating function sitting here. So this is appealing to the full counting statistics picture of quantum transport that I guess many of you are familiar with here. And we do this both for the injector and for the connection between the absorber and the bath. And then actually turns out, it's not really what we enforce here, but the cases we are looking at, it turns out that this generating function comes on a rather nice form. You can write it like this. So it's multiplied by the transfer rate of the particles. This is now for each of the two injector and bath parts. And then it comes as an integral over a distribution of the energies of the individual particles. So you have like kind of a double process. You first have particles coming, and each particle itself, they are coming stochastically, and on top of that, each particle has a stochastic amount of energy which is delivers to your absorber. So you have, let's say, two types of random processes on top of each other. And then the generating function comes like this here. So these are kind of the starting points for how we want to treat this fluctuations in the system. Okay, so then the proposed or the setup. So here is the, well, nice 3D slanted figure where we have the absorber is the green metallic dot in the middle and is connected via tunnel barriers to one superconductor, and to the yellow one is a thermometer. And there are a number of approximations here, and I should spell them out as much as I can, but one of them is that our thermometer is essentially non-invasive. So we are not now, in this approach, taking into account how the thermometer affects the state of the system here. But that can also be incorporated into our system if you want to. The left superconductor, well, here you have the kind of circuit-ish picture of the same thing that we have here. The superconductor to the left here is tunnel coupled, so this is our injector. This one we can either heat or we can voltage bias between this superconductor and another one here. So we can have, let's say, voltage biased and temperature biased injection or transfer of heat between the superconductor and the absorber here. The right superconductor is actually something which has a transparent ohmic contact. And this means two things. First, that the potential is just locked to the chemical potential of the right superconductor. So this contact here is much higher conductance than the tunnel contact here. And then it also means from a superconductor, what we know from superconductors, that they are perfect heat mirrors. So there's no heat can escape, but charge can move freely in and out. And therefore we don't need to worry about potential fluctuations, but only of temperature fluctuations in the island here. And then you have the different definitions of the coupling to the phonons and the tunnel conductance here. Something about time scales and assumptions here. So this hot electron regime, just to give you a picture, here is somehow 3 snapshots of the Fermi distribution. Here the green one is just when you had some tunneling event, so there is some energy. Sorry?
Just one, I beg your pardon. Yep. So you are neglecting any proximity effect from the right electron inside the island, right?
Yep. That is, of course, let's say on the picture here, did I write this here? No, it comes maybe late. Was it on the next slide? Let's see, I think I wrote this down somewhere. Yeah, right. So we neglect the proximity effect. And it's, of course, in the picture I wrote, you could, of course, say, well, does this really make sense? But in the setups that we were looking at, which Pichuk has been constructing, the absorber is not really a dot. It's more like a long thing where you have your mirror sitting a bit away from the other detection and injection places. So you probably don't have to worry much about the proximity effect. But this is, yeah, I think you're, I think it's
it can be useful also.
It can be useful.
Yeah, exactly. No, and we are now in a, maybe you will hear about this tomorrow, but we're also investigating this with dropping some of these assumptions. But as you know, then if you want to take into account non-equilibrium proximity effect also in this business, then you are on another level of complication of theory. So we are definitely, essentially, the quantum sits in the tunneling of heat quanta, and there is no quantum going on inside the metallic system, which just is a zero-dimensional node in this picture. Okay, so the picture here, you have here the green stuff is some particle jumping, and then you have energy deposited, and then over a very rapid time scale, you are assuming a new Fermi distribution with a new temperature inside the system. And this time scale is so fast, so we all the time assume that there is actually a well-defined electronic distribution with a Fermi-Dirac distribution with a well-defined temperature all the time. And then on a longer time scale, this energy then relaxes to the lattice on this tau scale. And also you are injecting new particles on a much longer time scale such that you are always injecting into a well-defined a system with a well-defined temperature. Then of course, if you want to do calorimetry, you are really careful about that your pulses don't come on top of each other, because then you have another problem. However, in the theory we are discussing, we are actually also, we don't really need this condition here. So the theory works well also for additional pulses on top of each other, which might be more interesting if you're looking at thermal temperature noise in the system rather than individual events here. Yeah, and there are also a number of other things which we are neglecting. For example, extra heating, which we know from early experiments that this is not really true. You typically heat a superconductor when you apply voltage bias and so on. Okay, something about these two components now. So we have the injecting part and we have the bath part. And then we want to have a statistical description of what happens. And then we start with the well-known tunneling formulas for an insulating superconducting normal conductor interface. And then we can look at the spectral rates for this to happen. You can tunnel in and out. You have your Fermi distribution functions shifted with the bias voltage, etc., etc. So this is, let's say, old school superconducting tunneling physics. So then the good news here is, as soon as you know this, what people have done before is to use this to calculate the charge transfer statistics. And the way to do this is to somehow take your original tunneling formulas and just hook up counting field terms. And this is now a bit technical, but you're putting up factors multiplying your rate so that you account for particles jumping back and forth of a superconductor if you want to look at charge transport. And in contrast to Thierry, we don't have a problem of going to energy dependence here because we are non-interacting particles. So the way to do this for energy is just that instead of counting charges, you're now counting energies. And the only difference for you who are familiar with these kind of formulas is that this generating function can be, say read out by saying, well, here you have your two rates, and they are multiplied by respective energy counting factors. And this counting factor contains a psi, which is so-called counting field, multiplied by the energy, and they are entering with different sides if you're jumping in or out of your absorber. And so forth, in that sense, you can immediately generate this function without too much thinking. And you can also then, if you want to do the derivatives to get your cumulants, and you see that your energy current and your energy noise come out as the stuff that you are expecting. So there is nothing strange. Yeah?
Here you assume the rates are independent of energy because simply they would be spread over a much larger energy scale.
No, the rates are dependent on energy. Yes, so I dropped the energy index there, but that was not necessary. You know, they are dependent on energy. So that's important to do. Otherwise, yeah. 5 minutes? Okay. So then I can calculate from this formula that I showed you before, I can calculate the tunneling rate, and I can also calculate the probability distribution for the energies of the individual particles tunneling based on this formula and the spectral rates I have here. And of special importance is that we can see, working if we have the temperature of the superconductor and the electron of the absorber to be much smaller than the gap, which are typically the interesting case when we want to operate this. We can find 3 different cases where the energies of the particles are well defined. And here you see a plot of the P of A. So you see somehow the spikes coming from the density of states now weighted by the Fermi functions, which gives you very sharp spikes. And in case 1, 2, and 3, you only see one spike essentially. The other ones are somewhere here in the on the very low level. And these are the limits where you really tune your system to inject individual energies or well-defined energies every time you jump. So then you you can simplify the formula I just wrote and come down to something like this, which tells you that you have a boson injection of particles, electrons with a well-defined energy every time. So you can tune your system both to control the energies of what you are injecting by temperature and voltage, and you can actually also control the rate at which is being injected, because the overall rate is then something that you control also with the voltage and temperature. So that's nice. For the phonons, we do the same stuff. So we take the microscopic picture, we have the electrons and the phonons, and you can then shuffle energy by creating and annihilating phonons, and then you can add this to the bath. And then you can go to your Mayhem textbook and just look what happens if you have 3D phonons in metals, and you can calculate, summing over all possible frequencies and so on, you can calculate the spectral rates, which are just the corresponding spectral rates that you have for a superconductor, which looks a bit complicated. They contain your sigma, they have velocity of the system, and there is some Riemann theta function, and then you have your Bose distributions, but this is kind of textbook stuff, so that's nothing that we are inventing. But the good news is that you can also again put this into the same type of framework and immediately write down the Cumulant generating function for transport of bosons, of energy quanta due to the interaction between the electron gas and the photons here. And you can actually calculate the cumulants, and we find a very nice and compact formula for this, which turns out to be exact, this formula, if n is odd. So if n is 1, 3, 5, etc. And if it's even, we are unfortunately not able to calculate this exactly, but we can show that this result is fine within 2% for arbitrary temperatures, and it gets better the higher n gets, so the larger the cumulant is. So this is, by the way, which I show on the next slide. If I just write out, you have the energy current here, which is some old result with the T5 exponent, and then you have the next order, the noise, it's a T6 exponent, and this nice approximation was already found out by Bayan and Jukka, and we now extended this to the arbitrary cumulant case here. So we have a very nice description of the phonon statistics also. Well, you can plot the same stuff. You can calculate the total rate, and then you can plot the probability distribution. And this is, of course, not as peaked and interesting as the superconductors, right? This is not our source of injection. This is our source of background problems, if you want to, right? And then you see that there's a broad range of energies where the phonons are, or where the energies are both absorbed and emitted. So if the temperature of your absorber is the same as the bath, you have your dashed lines here, you have the same amount, same weight for emission and absorption. But if you change it, you will have either more emission or more absorption, depending on which of the temperature is the highest. Okay, I guess I come to the last part. I had only a few minutes left, right? 2 minutes, yeah, fantastic. Full counting statistics in 2 minutes. So what we then did, yeah. So what we then did was that we wanted to look at the temperature fluctuations of the absorber. And one important point is that we realized rather soon that there's a back action effect that you cannot really neglect here. Namely, your rates to tunnel in and out depend on the temperature of the system. But since you don't immediately deposit all the energy somewhere, you have to take into account that if you tunnel in a lot of energy, after some time, the next one's tunneling now see that there is a higher temperature inside the system. And this means that the rates themselves will be modified. So you have to take this into account, and this is what makes this a bit complicated. Oh, well, it's pretty complicated. Fortunately, Andrew and some collaborators a decade and a half ago developed a very nice statistical approach for this, where you can, using some features of this problem, allow you to describe these full fluctuations, including this back action term. And we also used this before to look at the temperature in another system. So therefore, we can calculate that. I'm sparing you this since I have 2 minutes. There's no chance. It was not even planned to be in the original talk. So then there are the probability distributions of the temperature. And here the takeaway message is essentially that you see that if you are, now this is for zero voltage bias and for heating with the superconducting temperature, you can just see that you are shifting the distribution of temperatures away from the bath temperature in respective direction, depending on if you cool or heat your superconducting contact. And you also see that by trying to fit this to a Gaussian, that your fluctuations become highly non-Gaussian, maybe not so highly here, but you see more if you go deeper down into the tails. So was more kind of a way of showing that we can look at the full distribution. Then we are looking more at the cumulants, and these are now, although it might be technical, it turns out that you can use these equations and calculate. You get out the expression for the average temperature, and you can calculate the temperature noise. And I should point out now the temperature noise is not the thermal noise, right? The temperature noise is the autocorrelation of a temperature signal in time, which you correlate with itself. And as far as I know, there has never been such a measurement of this quantity. And this is, of course, it's not so easy to measure time-resolved temperatures, and then you should, on top of that, take an autocorrelator of this quantity. So already that one is a very challenging thing to do, but we just kind of also went through the third cumulant, and then we showed that this back-action I mentioned actually doesn't really occur in the second cumulant, but it occurs in the third cumulant and higher up. But of course, since the second one has never been measured, I guess one should start with that first before one tries the third one. So, okay, average temperature. Well, I don't have much time, so what can I say? We can derive the expressions. We can see that there are, as you would expect, some typical temperature and voltage values at which the system kind of exponentially sets on. So then you will see that your temperature goes exponentially large if you have a thermal bias on some Ts star, and actually your temperature starts to cool inside the system. You have this cooling effect, which is well known from before, when you hit a certain voltage V star here. And this also, by comparing this, the purple line here is actually the product of the injection time times the injection rate times the relaxation time. And if you really want to have separate events one by one, you should keep this inequality here, and therefore these T's and V's give you roughly when this happens. Well, I guess the chairman is already standing up, so let me then just flash you the last 3 slides. Did I lose some time with my computer mess up in the beginning? Yeah.
Extra time.
Oh, you're giving me extra time for that? Great. So how many minutes? No, I guess we're all waiting for lunch, so.
You're already after the extra time.
Even after the extra time. Okay. So you will hear more about this tomorrow for Bayern. Let me just jump ahead to the conclusions and just leave it with that. So thank you very much.
Thank you.